We are currently talking about the decorator pattern in order to move on to understanding the composite pattern thoroughly. It's not that the patterns are alike, however, they show two different ways of dealing with objects of a similar type. We just saw a piece of code which had basically a whole bunch of if statements, resulting in spaghetti code which was unmaintainable. If you notice that these if statements acted on different attributes of a file which are independent of each other, there is no reason why the processing of one attribute should depend on another. And here is where the decorator pattern comes in to help us. Let's see how Java works with input streams in this way using the decorator pattern. All input streams in Java derive from a common abstract class called input stream. It basically is a stream or a data flow which is used for input. This input stream contains standard operations which are shared by all streams no matter what the source. Standard operations such as close, read, reset are available as a part of the input stream base class. These are common across all input streams, no matter whether they are files, a network connection, a socket, or even keyboard input. Once we have this input stream base class representing all streams of input, for each type of input stream, there is a separate class deriving from input stream. We want the implementation details for each type of input to be handled in different classes. We don't want it to be all the same class, because why should file input stream, for example, know about object input stream? So we have a whole bunch of implementation classes, all of which derive from input stream. You can have an audio input stream which deals with audio, a gzip input stream which deals with zipped files, a byte array input stream which deals with input of the byte array type. Now, here is the crucial, super important part. Each of these objects that you see on screen, and there are many others, can be constructed from an object of type input stream. So an object of type input stream allows you to instantiate each of these different kind of objects. So input stream allows you to instantiate a file input stream, a byte array input stream, audio input stream, and so on and so forth. For example, if you had some kind of input stream object with you and you want to make it a gzipped input stream, you'd simply call the constructor of the gzip input stream and pass in the input stream object that you have into the gzip input stream constructor. Now you have a gzip input stream created from any other type of input stream. Now, because one input stream object can be created from another, you can have a whole bunch of these input stream objects chained together to get more input stream objects. So you start with one input stream, you instantiate input stream 2 with input stream 1, you instantiate 3 using 2, you instantiate 4 using 3, and so on. So you get a chain of input stream objects. This chaining of objects, all of which have the same interface or derive from the same abstract base class, to basically generate more objects of the same type, again deriving from the same base class. And remember, in our example, this base class is input stream. So this chaining of objects to get more objects of the same base class is basically the hallmark of the decorator pattern. The decorator pattern, if you remember early on that I compared it to layers of an onion, there are multiple layers to this onion. Each of these layers are the same base class or the same interface, and they're chained together one within the other. every layer is still an onion, and in our case it's still an input stream, but they are chained one within the other to generate more onion or more input streams. Moving on with our example, suppose that we wrote some code that saves objects, that is Java objects, to a file and then zips that file. So we have a file which has Java objects saved in it and it's zipped. Now, saving objects to a file is a very standard operation in Java. People do this all the time and Java makes it extremely easy. This is done by a standard process called serialization. So serialization involves taking any Java object and writing them onto file. Now, when time comes to use these objects, these serialized objects which are zipped and they exist on disks, we need to perform the reverse operations. We need to unzip the file first and then read in the objects and then use them. That process is called deserialization. So first we unzip, then read in the objects and use them. Now in order to be able to do this, we create a chain of input stream objects like we discussed earlier. We look at some code here rather than just talking about it in theory. So notice how this chain is built up. At the very core of this chain is the file input stream, because that's what we're dealing with, files. So we have the file input stream and serialized object just happens to be the name of that file. It's then passed into a buffered input stream which allows us to buffer it into memory, and then we unzip it using a gzip input stream. Now we have an object representation in serialized form and we use the object input stream to get the information out of this object, serialized object. Now if you look at how this code is set up, at any point in time, now we are only dealing with the outermost object. In our case, it is the object input stream. We only assign a variable to hold the outermost object. We don't really care about the inner objects. The inner objects just do their work. We just hold the outermost layer of the onion. Then, in order to get the object out, we just call read object on OIS, that is the object input stream, and then close it. Now, it's very important that these decorators and each of these classes represent a decorator be independent of each other. No decorator should know the exact type of the other, only that they have a common interface or abstract base class. So they are chained together, but they perform their operations independently. No decorator knows that another one exists or expects another one to be there in that chain. One of the important things about the decorator pattern is that each decorator object which decorates the input that it's passed in is independent of any other decorator objects that exist in the system. Basically, you can take a decorator unit and then mix and match it with other decorator units. Each chain can have a different set of decorators. They don't know about each other. They only share a common interface or an abstract base class. Now that we've seen what the decorator pattern does, let's analyze when we'd want to use it. So in general, we'd use the decorator pattern when we have lots of objects. Each of these objects have a specific behavior independent of all others. They may be acting on the same thing, but the behavior that each of these objects exhibit is completely independent of other objects of the same type. These objects are the same type of objects. Each of these classes can be constructed from an object of the common interface or the base class. All of them share an interface and a base class and can be constructed from any object which has that interface or base class. And in our example, that base class is input stream. Decorators, the way they are used is by chaining them together. Each element in the chain should not know of the other objects that exist in the chain. This allows us to mix and match the elements and string together a stream of decorators in any order. They have a common interface or abstract base class, each of these decorators. And the type of behavior that determines whether we have an independent implementation of a decorator. So there is one class for each independent type of behavior. Let's reinforce the onion analogy a little bit so it's very easy for you to remember what a decorator looks like. So you have at the core the file input stream. You pass it into another layer, which is a buffered input stream. All of these are input stream objects. Now we want to unzip it. So you'll pass it into a gzip input stream. Now that you have the unzipped object representation, you want to be able to deserialize the object, which you'll do using an object input stream. Now, a bunch of these objects, all of these implement the input stream interface. These are the layers of the onion. Each of these objects can be created in a chain from one preceding object of the same type. The buffered input stream is created using a file input stream. Gzip input stream is created using a buffered input stream, and so on and so forth. As a user, you only ever interact with the outermost object, which in this case is the object input stream. So the user only interacts with the head of a chain, if you assume this as a chain rather than layers. This diagram sums up the decorator pattern. Whenever you want to set up a decorator pattern in your code, if you have code which can be broken down like this, it's a classic use case for a decorator. Remember the crucial bit of information. Each of these chained objects work completely independently of the other. The behavior that they use to decorate what is passed in is independent of other links in this decorator chain. This was the decorator pattern, where all objects within the pattern formed a nice, neat chain. At any point, you only need to deal with the head of this chain, and the remaining objects in the chain just decorated the one passed to it by themselves. The remaining objects dealt with themselves. Now, what if we wanted a set of objects whose relationship wasn't this nice chain relationship, but looked something like this? Okay, you'll see that we have way more objects over here, and they have a pattern which isn't really a link or a chain. Note these arrows. They seem to be pointing upwards. This is definitely way more complicated than the decorator pattern. We'll see what emerges. Right? Whole number of objects, a lot of inheritance going on here. Let's see what structure emerges. What if we had a whole number of objects whose relationship looked like this? There is no way the decorator will work here. Firstly, the classes themselves are no longer independent of each other. If you look at them, there is a clear inheritance and there's a clear dependence on one another. Also, the user no longer can work with just one of the objects here. The user needs to interact with every one of them. Also, the user needs to interact with the entire object set as a whole. The user needs to interact with all classes, not just the outer one. The user needs to deal with each class independently, And also, the user needs to deal with all classes together as one whole. As you can see, the underlying requirements which make the composite pattern necessary is completely different from that of the decorator pattern. However, it has one feature that is still useful to us. Objects are created from objects like themselves. That is, all objects in the composite pattern as well share the same interface. All of these together is pretty much the definition of the composite pattern. The composite pattern speaks of objects which are all like themselves, share the same interface, they have a whole bunch of interrelationships with each other, and the user needs to be able to deal with every object individually and the entire composite as a whole in exactly the same manner. If you've ever dealt with UI containers, especially in a programming language like Java, that's pretty much the composite pattern. You have the entire UI as a whole, which is the composite, and you have individual UI elements within the container. The way the user interacts with the individual UI elements is exactly the same as how he interacts with the UI as a whole.